Hello, everybody. I'm Randy Stott, Managing Editor of Gear Technology and Power Transmission Engineering magazines. Thank you all for coming for Ask the Expert Live. Today we have an open session, so feel free to ask any questions you like. The way it works is this: if you've got a question, just raise your hand. I'll hand you the mic. You can ask the experts. But before we begin, I'm going to give each of them an opportunity to introduce themselves so that you can better know who we're dealing with.
So, hello everybody. My name is Carsten Stahl. I'm head of the FZG of the Gear Research Center at the Technical University of Munich in Germany. The FZG is doing research in academia since 1951, so more than 60 years, and I, as a person myself, am doing research and application in industry with gears for over 20 years.
I'm Chuck Schultz. I'm a consulting engineer. I have my own little consulting firm, Beta Gear Service, offering general services in the gear trade, designing, evaluating, inspecting gears. Been involved with gears since 1971. I also have the privilege of being the corporate blogger for Gear Technology magazine.
My name is Hartmut Müller. I'm Chief Technical Officer of the Klingelberg Group, and I'm in the gear business since 25 years.
I'm Octave Labath. I am a consulting engineer. I retired from a gear company in 2001, and I had been there 39 years when I retired. So I've been involved with a lot of AGMA committees. I'm currently chairman of the AGMA Epicyclic Gearing Committee, and I enjoy gears. I don't like gear wear, like sweatshirts. That's a bad use of the word gear.
There you go.
But you did go from being tired to retired.
Okay.
Thank you, gentlemen. Today we have an open session, so the topic is Ask Anything, and we're going to challenge these guys with a wide variety of questions. I have a few from the readers, and I'm going to start out with one of those. What is the optimum case hardness for carburized gears?
The default values are 58 to 62 hardness Rockwell C. At the case, opinions vary on the core hardness, but the allowable stresses that we have in AGMA are based upon 58 to 62 at the surface, with somewhere in the 30 Rockwell range as a core hardness.
Agreed. It's basically the same with bevel gears. We recommend 60 minus 1 for the ring gear, 60 plus 1 for the pinion, since the pinion has less teeth and is a little bit higher loaded concerning flank stress. And the same with the core hardness, about 350 Vickers, something like this. This is what we recommend.
Chuck, tell them where the core hardness is measured.
With a specimen.
No.
Or we kill the gear.
That's the effective case. The core hardness is measured at the root line, in the middle of the tooth.
Yeah.
Center line, the intersection of the center line of the tooth and the center line of the root, or the root diameter.
Thank you, gentlemen. Next question from a reader. How do you inspect for grind temper on nitrided gears?
I would not inspect because I would not grind nitrided gears, except the customers recommends this. But I see a high risk in grinding nitrided gears because the case depth is so small, and if you grind a bit too much, everything is lost.
The general practice with nitrided gears is to grind them before nitriding.
Yeah.
And the distortion in gearing comes during the quenching operation. Since nitriding is slow cooled and there's no quench involved, whatever loss of accuracy is viewed to be quite minimal. And again, the shallow case that you can build up just doesn't lend itself to being ground off.
Yes, and the cost for nitriding are much higher than for carburizing. So it only makes sense if you really need it, and you need it if you don't want to grind after hardening. So the combination, even if the customer really requires it, I would to try to find out why you would grind a nitrided gear. It doesn't make sense.
Again, as I stated yesterday, the customer is not always right, but he's always the customer. I had a customer who required that the nitrided gears be ground. I was told that you cannot nitro etch a nitrided part.
And another thing is that the application of nitrided gears, we don't recommend them if you have a high root bending stress. We recommend this if these are very fast running gears where you only have the focus on the flank wear and not on the root.
Thank you, gentlemen. On the same subject of nitrided gears, I have another question from a reader. Why do nitrided gears have low resistance to shock loads?
It's only low in comparison to carburized. Generally, we're looking at the strength of nitrided gears based upon the core hardness, which will be somewhere in the 26 to 32 Rockwell range. Not that dissimilar to what carburized core hardnesses are, but we also don't tend to nitride very coarse pitches. The K-steps are so shallow, and they're generally there only for wear purposes. So, between the shallowness of the case and the fine pitches that are involved, they appear to be relatively weaker in strength, in bending strength, but actually the allowables are not that much different.
And another thing we also observed is that the crack propagation is different in between carburized gears and nitrided gears. The crack propagation goes much faster on nitrided gears than on carburized gears.
You might compare it the difference between an asphalt road and a concrete road. The asphalt road, being the nitrided, will peel off very much more quickly than the concrete road will.
The other thing is the case on a nitrided part is brittle. It's also brittle.
Yes.
In fact, I've seen nitrided parts chipped before they ever went in service.
Thank you, gentlemen. Next question from a reader. Is there a non-destructive inspection method for detecting case depth in carburized, induction-hardened, or nitrided gears?
I think that is a dream of every metallurgist on gears. There are methods with magnetic measurement tools to do something like that, but it's never accurate. So I have not heard about a method which is really accurate, because you also have to define not only the depth, you have to define the value, what the depth is measured for. Like in DIN in Germany, it's usual to measure against 550 HV, and to adjust a system which is magnetic or with electric resonance in the material to exactly that value would not be accurate.
The only way of non-destructive measuring is to take a specimen and kill it afterwards. But then you need to have the same temperature gradient behavior of the specimen like you have it on the gear, which is all mystery. We have to do this for classification societies, for ships, for ship drives. But if an honest answer is we just do it until these guys are satisfied, I doubt the technical reliability of these processes.
We had a project recently that had 17 engineers from, I think, 8 different countries involved with it, and we ended up with 13 different heat treat coupons in the furnace with the parts. And in the end, the results really didn't vary all that much from the different methods, but everybody had their own opinion as to, whether it needed to be a slotted coupon, whether it could be a round coupon, how big of a coupon it needed to be. What I tell my clients who are not gear makers is that if you tour a place that's making carburized gears and you don't see cut-up samples, don't buy gears there. Because if you're not cutting parts, you don't know what your results are.
I fully agree.
Thank you, gentlemen. Next question from a reader is, how do sintered composite gears compare to case carburized gears?
Maybe I start with it with the answer. There is no either or. So you can sinter material and carburize and harden it. So there is not a either pulver metallurgy or standard steel carburized. If you carburize a sintered gear, then you have, of course, some porosity, some air bubbles in the material. This goes down to, I think, the best you can get if you compress on the outside to 3%. So you can reach nearly the strength values of steel gears if you have an extra compressing step in the production. You will never exceed it, so it's not possible to get higher, but you can get close, which is about 90 to 95% of the strength values of steel.
There's a big difference in the structure of the material for a forged part, carburized, versus a centered part that you're going to do anything to.
Yes, but I have a very little question mark about the so-called big advantages of forged blanks. I don't see a huge benefit in forged blanks from the structure, because you cut a lot of slots in it and you kill all the lines of the material. I think the big advantage is that you save a lot of money in turning.
Well, we probably need to get our friends from the Pressrite booth over here to fill us in on the near net shape forgings, which are considerably different than a sintered part. The sintered parts have made tremendous progress in recent years and are getting to be used in many more higher stress applications. There's a lot we don't know about gears. We've been at this for a couple of thousand years, and we probably have a couple thousand years of questions to work on, and the sintered parts are certainly an area that are going to get a lot of study in the years ahead, because they do have a lot of cost advantages.
But I also see a certain potential, not just in sintered parts, but also in 3D printed parts. If you take a smart material gradient, you could even improve. I think it should be able to improve the load carrying capacity.
Thank you, guys. As long as we're talking about materials, I do have another question from a reader that's related, and that is, why aren't more gears forged?
Well, first of all, a lot of gears are forged, and you just don't realize it. Most bar stock below 10 inches in diameter can be considered forged. You can get a real good argument going in a room full of metal, or just asking about what reduction ratio is needed, and they'll probably never reach a conclusion, and unfortunately no one's in a position right now to fund the research on anything other than laboratory-sized parts with the difference between forged parts and raw and I guess less forged parts, shall we say. Almost anything you make for a laboratory, the bar stock has been forged.
So in my industrial experience, I did a lot of tests with ring gears forged, near net. I think we're talking about near net shape forged. And it was at the end a calculation. You reduce a little bit the material, which you cut away other way, but also you need some extra time and extra effort to find the slot, and you have indefinite tool life, which you need to cut away the exterior of the near net forged surface, which adds stress to the tool, and the tool life differs. So we did not see advantage at the end when you count all the numbers, the extra cost for the forging, the extra effort to define the tool life, and to find the slot against cutting with high speed into the full material. So it was a zero number, and we did not do it.
On bevel gears, there are some applications with forged ring gears, but if you think since you always have to design a gear set, one thing is very important. You need to get the pinion out of the die. So this is a pretty hard limitation for the gear design itself. You are limited in your spiral angle. You are limited in your cone angles. This is one reason that makes it difficult. Another reason is, like Professor Stahl mentioned, the bigger the gears are, the more it seems to be favorable. But what happens? We need to, if we put it on a machine, we need to make a very complicated stock division, not just on one gap, but maybe on 3, 4, 5, 6, 7, 8 gaps around the circumference. We hope that we found the high spot, and then we have a little bit extra way in the plunging depth. At the end, the time we could save instead of cutting from a solid blank is just wasted by stock division. And another thing is we have to cut through this very hard skin, which comes out of the forging process, and this is something which makes tool life a little bit unpredictable.
Yes.
So at the end, I think for ring gears in a passenger car axle, maybe 10-inch, 8 to 11-inch, it will work, and there you might have a reasonable time saving. But for bigger gears, for truck gears up to 500 millimeter, I think dry cutting technology made such a big improvement with carbide tools that the time saving is neglectable. We just waste the time saving with stock division.
Yes.
We can remove stock so rapidly now with gashing cutters that on some parts we're spending more time getting the chips out of the machine than we are cutting the part. So the advantage of having a net shape really wouldn't appeal to most people unless you got to the point where you were so near net shape that you could take the part, carburize it, and grind it without having to touch a hob.
That's my dream.
If you could do that, people would line up. But as long as you have to have the hobbing step in there anyway, it's not worth the expense and the aggravation.
Yes.
Thank you, gentlemen. Do I have any questions from the audience? Moving on. From a reader, I have this question. Between a straight bevel gear, a spiral bevel gear, and a hypoid gear, which one can transmit the most load and which one is quietest?
Well, definitely the straight bevel gear will not be the quietest. It's just a question of contact ratio. The higher the contact ratio, the smoother a gear will run. On the other side, if you compare a hypoid gear set with a bevel gear set, the hypoid gear set has the advantage that the pinion gets a little bit thicker. You have a fatter pinion just because of the hypoid offset if you take the offset into the right direction. This means the offset should always go into this way that the spiral angle of the pinion will increase and not decrease. This also helps in load carrying capacity concerning root stress, but you lose, of course, a lot of efficiency if you add offset to the gear. And concerning the noise behavior, that's difficult. The answer is not a clear yes or no. If you have a hypoid gear set can easily be lapped. And the beauty of the lapping process is that you have an inherent removal of material which will somehow hinder a smooth meshing. So after lapping a hypoid gear set, you have a very smooth meshing of the flanks, a very smooth contact. You can do this also by grinding, but in grinding you need to design this into the flank form. If you don't design it in the flank form, the gear will be lousy loud. So this is one of the big differences. But nevertheless, grinding makes more and more progress because you can control the geometry perfectly. You don't have to struggle with heat distortions. You don't have to struggle with potato chip back faces of ring gears. And load carrying capacity is definitely higher for ground gears. And the load carrying capacity will be highest for hypoid gears since we have a fat pinion.
One of the remaining large influences on all bevel gear sets is the quality of the mounting and the quality of the assembly adjustment. And you can make very good bevel gears and give them to people who are not proficient at mounting them, and it'll sound like a rock crusher. and they won't last very long when they're noisy either. So many times people need to figure out what their real noise generator is. Is it the quality of the gears, or is it the quality of the assembly and adjustment on the bevels? So before you give up on a set of gears, have somebody that really has the touch for adjusting them work on it.
And I fully agree. In most cases, it's not the bevel gear set itself that makes the problem. In most cases, it's somehow the environment. And what we strongly recommend is you need to make a comprehensive design. This means you need to take into account the bending of the pinion shaft, the bending of the gear body, the bending of the bearings, the bending of the housing, so that you get reliable deflections. For every load case, you have different deflections. And once you have this, then you can optimize your flank form. Just flank form optimizations picked by the blue, this is just for conferences, but not for real life.
We had an example many years ago on offshore powerboat racing where the gears were aircraft quality going into the boat, and they wouldn't even last in a single event. And upon further examination, it was discovered that when you had 2,000 horsepower going into this aluminum case, the thing distorted all over the place. So by careful analysis and modeling, they were able to determine what it looked like in a running condition. They changed the way that the gears were made and lapped to one another, so that if you looked at the bluing coming out of the tester, they looked like a horrible set of gears. But when you put them into service and they were operating in a distorted case, they could not only finish an event, they could finish a second event and sometimes even a third event with simply changing the mounting that was built into the gears to match what it was experiencing in the field.
Ladies and gentlemen,
I have another funny experience with a load carrying capacity of bevel gears and also with the noise. This was a ship thruster drive, and all of a sudden we had pittings on both sides, on the drive side as well as on the coast side, which should never happen because the propeller only runs into one direction. And we really didn't understand it well, but at the end we figured out that it was a design issue. The design engineer made the radial axial bearing at the top of the pinion shaft. This is easy for assembly. And just the radial bearing near the crown of the pinion. And the pinion shaft was 1.90 meters. And the boat was running in ice conditions in the Northern Sea. So the oil temperature was about 70 centigrades. The housing temperature was about 4 centigrades. And the only thing that happened is that the pinion got longer, and then we suddenly had interference on both sides. We didn't have backlash. At the end, it might be something easy like that. So we said we would change the design, but as you mentioned, the customer doesn't have always right, but we have to respect him as a customer. So what we did is we increased the backlash by 1.5 millimeter, and everything was perfect. I just want to stress you need to make a comprehensive design, not just focused on the flank, but you need to take into account everything.
I would like to add something to the question, influence of the hybrid offset on noise. Nearly every OEM car manufacturer is trying to reduce the offset due to efficiency. So if you reduce the offset of the hybrid gear, the efficiency gets better. But the limit is noise. So when you reduce the offset and you're assuming you did everything right on the axle before, and you do everything right on the axle with a reduced offset, it becomes more and more difficult to get the NVH issues under control. So it's clearly everything you do against efficiency is good for NVH.
I don't agree to 100% because I think it's important if you compare a lapped gear set to a ground gear set. If you're talking lapping, you are absolutely correct. Yeah. For a ground gear set, I think it's also possible to make a noise reduction on a ground gear set for a bevel gear set. You don't need necessarily a hybrid gear set.
It gets more challenging. In any case, it gets more challenging.
That's right. It's more challenging, yeah.
Thank you, gentlemen. Next question is there a reference and an example calculation for short pitch hobbing?
For those who aren't familiar, short pitch hobbing is the use of a tool with a lower pressure angle to cut apart and avoid an undercutting situation. I myself am not a tool designer. I do design a lot of gears and a lot of gearboxes, and the first thing I try to do is avoid having any situation where I have to have a short pitch hob made. But sometimes with legacy designs or other considerations, you do have to have a low numbers of teeth, and you end up having to have a tool made. It'd probably be very worthwhile for us to look into getting a nice article written demonstrating how this is done. Maybe we can get one of our tooling friends to produce something, because it does come up a lot, and it works wonderfully, but it's not necessarily the best answer to all the problems.
Yeah, but that's right. But it's a good answer to improve tool life.
Yes.
Because you have a different movement of the tip of the cutting edges. That this so-called trochoid form will change with a short pitch hobbing, with a short pitch hop, and you can improve tool life and you can improve the chip flow. Mm-hmm. That's basically what it helps. And sometimes if you don't have the proper pressure angle, you can tweak a little bit with this principle and use a different pressure angle on the part than you have it on your hob.
Very good. Thank you. This next question is a little bit long, so I'm going to bear with me for a second. I'm going to read through it and get your feedback. In the last 10 years, continuous generating tooth grinding has been used more and more for gear finishing. However, our background teaches us to avoid finishing the gear set by the same technology due to noise issues. What is the recommendation nowadays for commercial vehicle transmissions? Can generating grinding be used since the process feed rates and number of starts are different in the gear set? Or are there other important considerations?
This is the reference to the infamous ghost frequency days. We would have gears that would look wonderful on the charts, pass every quality requirement that was on the drawings or in the specifications, and we put them in a gearbox and they would sound horrible at some frequencies. A short-term fix was to make sure that the gears and pinions were ground on different types of machines. For example, you might in those days we might have ground a pinion on an electronic rice shower and the gear on a mechanical rice shower. We later traced some of this to internal machine characteristics related to the number of threads on the main drive wheel, the number of threads in the grinding wheel, some fairly complex mathematics that made your head hurt just talking about them. The new machines have a lot less mechanical parts in them, so there's a lot less opportunity for these ghost frequencies to occur. And gee, it's been years since I've heard anyone have a complaint about it. So,
we have a research project where we do the opposite thing. So we apply waviness on the tooth length with a very low amplitude, so it's far less than 1 micron, to superimpose noises to reduce the main noise. Meaning that a very small amplitude is enough to get a high-pitched whining noise when you have waviness on the teeth. But today I agree that this is something from the past. Today with a fine measurement, when you have 25 times 25, you can measure and you can find waviness on the teeth. And also with single flank testing, you have the opportunity to identify the waviness. And certainly you have to match the angle of the tool, of the worm grinder, so that you do not have all in the same phase. So today we have tools and methods to avoid ghost frequencies or high-pitched noise from waviness.
I agree that the mechanical machines had a lot of possibilities to impose ghost frequencies. Unfortunately, this is also true for electronic machines. With the direct drives, you can make any ghost frequency you want. You just need to change the parameters of your servo drive, and you will have results that are unbelievable. What we figured out is that this is all to micro undulations on the flank. We are talking about sine waves with 0.2 micron amplitude. You can definitely clearly hear them, and if you, in this case, we don't believe to the SFT measurement. We take the structure-borne noise, but then you see the first tooth harmonic, second, third, fourth, and so on. But suddenly you see something in between, and these are the so-called ghost frequencies. And these ghost frequencies, they definitely come out of the process or out of the machine. The question is, how can you figure out what's wrong on the machine, what's wrong with your process? And this is a very, very complicated simulation tool. We designed something like this. We are still not yet 100% finished. But imagine if you have not a properly balanced threaded grinding wheel. You will have ghost frequencies for sure. And the task is now to find a correlation in between the amplitude and the frequency of your micro undulations on the flank and what's happening on the machine. I'm always a fan of having something related back to something which you can geometrically inspect. If you go to structure-borne noise, I don't know what to do. I just can say it's good or it's bad, but I don't have the possibility to feed it back into manufacturing. So we think the task is to develop a measuring principle to detect these micro undulations and to find the root causes for these micro undulations.
And we think gears are complicated. If you talk to people who have devoted their lives to surface finish measurement and evaluation, I don't know how they stay sane. There's so many different vectors going every which way and measuring. And if you've had the opportunity to watch a modern CMM machine that's fitted with a profilometer for measuring surface finish, and just the variation that can be seen in that relatively minor improvement in technology, we have a lot to learn about what's going on the tooth flanks. But for right now, we have to make gears and ship them.
So do we.
So,
Thank you, gentlemen. This next question comes from a reader who also happens to be in the audience, but I'm going to go ahead and read it. We may get some interaction here. Is it possible to indicate the diameter over pins or balls in a double flank gear tester?
So everything is correlated together. The tooth thickness, the double ball measurement, the double flank measurement. So when you have a master wheel in the double flank measurement machine, which is accurate, and you know the contact pattern between the master wheel and the test specimen, you can calculate back and forth to the double ball measurement. So that's possible. But every time when you calculate forward and backward to something, you need first to make sure that you don't have any cross interactions, so maybe a wrong contact pattern, and certainly you are losing accuracy on the way. So you can't expect that you have exactly the same value at the end, because you are assuming many things on the way forward and backward. But generally, from geometry side, it's possible.
Maybe I have a lot of enemies after my following statement. I don't like the DOB measurement. I think this is something quite obsoleted at these times where you have a ball and you press it into your gear to look basically how the runout is. I think with modern CNC inspection technology, you can tell something about spacing left flank, spacing right flank. You can calculate something like a runout. But what is really the purpose of dimension over ball? In my point of view, the only purpose of the DOB measurement is to fulfill what's written on the drawing. But I don't see a real technical need for the DOB measurement.
I've always been more in favor of using span measurements myself, because when you deal with larger parts, you don't want to have two guys and a crane to do the measurement over pins. And a span measurement, as long as you have accurate tooth veneer or accurate veneer caliper, you're good to go.
So would you say that it is correct to do that, or is it incorrect?
It can be done. The question is whether it should be done.
Are there any standards to cover that?
We got any fine pitch guys here? No. Octave? No. Where's Bob Smith when we need him? We need to throw that one to Bob Smith and get a written answer from Bob Smith. Bob is the absolute dean of the fine pitch world, and whatever he says, I'd go with.
I mean, you find calculation method in DIN 3961 that you can calculate up and down. What you cannot find is the tolerances and the machining errors. And the purpose of these measurements is to find machining errors. So when you calculate forward and back again, you can calculate the theoretical geometry, but you mismatch probably what you want to measure. And at the end, this is what Dr. Müller said. The part does not need a ball measurement. The part needs a run out or a good transferring behavior, spacing behavior. And everything you measure, either with a flank tester or with balls, is just a help measurement to have something you can put in your drawing. So again, from my point of view, it does not make sense to put something in the drawing and you measure something else and calculate it back. It just makes no sense.
The composite measure is an excellent, fast way of checking the gears. Unfortunately, with a double flank inspection, first of all, the gears are not running on both flanks, and you're combining a whole lot of different things when you do that. To me, it's kind of like it's making sausage. You've taken all the ingredients, the run out, the spacing, the tooth thickness, and you've mixed them all together, and you come up with the results. Now, if the result may be to your taste, it may not be to your taste, but you can't really, from that result, say, well, that was a little bit too much spacing here, and it needs a little less run out. You can't really do that from the composite. It's a great, efficient way of handling a lot of gears in a very short period of time, but it doesn't really help you refine the process of making the gears to improve it.
And according to my opinion, the double flank measurement is just used to detect nicks or burrs or any dirt on the flanks. That's the main purpose for.
I'm going to take advantage of the Ask Anything format. Aside from aspiring to become engineers, can I ask each of you what motivated you to enter the gear industry?
So who starts? So I started 21 years ago with my start as a PhD in the FZG Gear Research Center, and I found and still find gears fascinating. It's a machine element where the thing applies. The more you know, the more you don't know. So you're never ready. And I always find people telling me, why are you working with gears? The gears are there for thousands of years. He's right, but we should stop any research on medicine. Medicine is there for more than 1,000 years.
I needed a job. I applied for an apprenticeship at Falk, I applied for an apprenticeship at Harnisch-Fager, and I applied for an apprenticeship at Harley-Davidson. And I nagged all three companies 2 or 3 times a week over the phone. And Falk gave me an interview first. So I ended up in the gear business. And I've regretted a day of it.
Well, I studied electrical engineering and made my PhD in microelectronics, and then I wanted to make something real hard. So I went to the gear business, and I never regretted this step. As Professor Stahl mentioned, the more you know, the less you know. And this is really challenging, and I think it's the most challenging area in machine elements that you can ever think about.
Let's see. It was time for me to get a co-op job. The co-op coordinator said, "There's a gear company looking for a co-op. Would you go out there?" Yeah, so I went out there. Walt Rye hired me as a co-op, and I've been there ever since. I don't regret any of it. I've enjoyed gears, but I'll tell you something. With gearing, you learn something every day, including today.
Thank you, gentlemen, for sharing. I've just got a couple more questions from readers, so if anybody else has something from the audience, please raise your hand and I'll get the microphone to you. Next one is, in a sintered steel hob tool, what are the advantages and disadvantages of working with high cutting speeds with low feed rates versus low cutting speeds with high feed rates, considering the same cutting cycle time of the machine?
So I just start because the option is there. I played around very lot with exactly these figures. I had the chance with BMW and support from Klingelberg, by the way, about 15 years ago, to play. And I found that you cannot answer this directly. So there are some steel and geometric combinations which like more feed. You can tell from the marks on the tool that you have to increase feed, and others where you see from the color of the chips and from the behavior and sparks flying that speed is too high or too low. I have not found a very scientific answer to that. I think the combination of the steel grade, the hardness, the coating, and the material constants of the cutter, there has to be found an optimum by me saying that as an academic trial and error.
Our experience is it's not so very clear, but the trend we see is that the harder the cutting material is, and let's now talk about carbide. Carbide likes very fat chips, and if the chip thickness is not high enough, carbide doesn't perform good. So you need to have a rather fat chip, and then you need to have, of course, a cutting speed that is quite reasonable. I'm not talking about 500 meters per minute. This is far beyond. But for a type of passenger car, rear axle, something between 200 and 300 meters per minute, this works fine. The bigger the module becomes, the slower you have to go with the cutting speed. If we make, for example, a 2.5 meter ring gear for a ship drive, we only work with a cutting speed of 140, 150 meters per minute, because otherwise we would have a too high thermal impact to the cutting edge, which will kill the carbide. It will not kill the coating, it will kill the carbide underneath the coating. So the experience is it's all because of the thermal load, and the lower the thermal load is, the higher you can go with the cutting speed, but you always need to have a reasonable chip thickness.
As we move to more environmentally conscious manufacturing processes, the whole equation on feeds and speeds changes. What we're trying to do is we're trying to drive all the heat to go out in the chip and not remain in the cutter or in the part. And when you get to the point where you have that right, you don't even need to have a coolant on it anymore, which saves a lot of energy, a lot of environmental mess. But these are questions that really need to be developed on a case. The answer has to be developed on a case-by-case basis, because there's power limitations in machines, there's rigidity issues, the part geometry is always unique, the materials are unique, but it is amazing companies today don't view engineers the way they used to. Companies used to consider engineers their most valued asset because the saying was a good engineer saved his own salary every year. Now companies tend to view engineers as more of a liability, but this testing and process development is an example of an area where a good engineer can go in and develop a solution that will have lots of cost impact on a company. And this kind of testing needs to be celebrated a little bit more. It isn't just a matter of looking in a book.
Thank you. I've got one last question from a reader, and it's kind of in-depth, so bear with me. I'm going to read through this and see what you guys can come up with. If there's an angular relation specified between the missing tooth of an internal spline and the tooth thickness center line, then which should be machined first? The internal splines or the external gear cutting? If we machine the internal splines first, how do we get the angular relation? Or if we do the external hobbing first, then either broaching or wire cutting the internal splines might lead to a helix angle error. Please advise.
Next question.
I think the gist of it is, how do we locate the external gears to the internal splines if there's a timing element involved, and make sure that they line up correctly?
It's a lot of fun, especially if there's helical parts involved, because then you have to consider the reference plane to where the alignment is specified. CMM machines make it possible to measure things a lot more. Don't really help you out in the machine shop of putting the feature in.
They'll tell you missed it.
They'll tell you missed it, but they won't really help you figure out how to put it in there. This is where really clever tool designers help, and really clever programmers who are able to go in and probe the right surfaces in the right location and direct the tool into the proper spot. Had a lot of jobs over the years with holes aligned to keys, gear teeth aligned to keyways, and there's always a certain amount of trial and error involved. With regard to which one you do first, it really doesn't matter. A lot of people have brooches, for example, that already have the missing tooth figured into the brooch. So in that case, the decision's already made for you. It's one of those areas where we quote our favorite consulting engineer, Mr. Ray Drago, it depends.
One of the things with this is you're talking spacing. You really don't want to match the spacing. You want to match the loaded flanks.
Yeah.
And when you've got two different pitches, it's not that easy.
Thank you, gentlemen. Are there any other questions from the audience?
I'm back on the double flank gear rolling tester. Is the R&R study the right method, or the measurement uncertainty is the right method to decide the acceptability of the measurement system? Shall I repeat the question?
Yes, please.
In case of a double flank rolling tester,
Yeah.
there is an R&R, reliability and repeatability test, which is carried out, and the other one is measurement uncertainty calculations. Which is the right method to decide the acceptability of the system?
It's a complicated field you are addressing. For what purpose would you like to make the double flank test? Would you like to have some readings about the run out of the gear, or would you like to detect errors on the gear, like nicks, burrs, or dirt on the flank?
Yeah, to detect the errors on the gear.
To detect the errors.
Errors on the gear during production.
Well, if you make a double flank test, I would include not just one master gear. I would include another master gear which has a cardanic which is fixed cardanically, so that you can see the FH beta error, and that you can see conicity of the gear. This would be free of charge. This would not take more measuring time. You have, for example, imagine if you have an internal gear, one master gear on the left side and another master gear on the right side, and the right master gear only has teeth at the top and at the bottom, and this one can tilt in this direction and this direction. Then you get a little bit more than just the information that how the runout is. Then you get information about FH beta, and you get information about the conicity. This is some customers do this. For example, ZF, they do this for their automatic gear transmission for the HAP gearbox. This is a very reliable system. We made GR&R studies, which is all we have to keep very tight tolerances. But nevertheless, the problem will always happen if there is some dirt, because this is a very complicated measuring, and you will detect dirt immediately. But what happens if this dirt comes into this inspection machine? Then maybe the next 10 gears will be kicked out just because of another problem. So it's as I mentioned, I like geometrical measuring results. I don't like running measuring results.
What pitch are you checking? What size teeth?
Well, these are gears for two-wheelers, the small gears. Gears for two-wheelers, motorcycle.
Okay, but I mean, what size teeth?
You mean number of teeth?
No, is it like 2 module?
A module of the gear?
Yeah.
Yeah, less than 2.
Less than 2.
Yeah, I think my preference would be to have a modern elemental gear inspection machine that could be programmed with acceptability limits and run the parts through that, and have a lead and involute spacing run out rather than a composite check.
I fully agree with him, because you don't get a feedback to your production out of the double flank test. But you can get a very clear feedback out of geometrical measurements, profile, lead, and spacing. This gives you a clear feedback to your production what needs to be optimized if the gear would be out of spec. The results of a double flank test is, like he mentioned, it's cooking sausages, all ingredients in, and you like it or you don't like it. But you don't get a clear. It's nearly impossible to get a closed loop feedback to manufacturing.
Thank you, gentlemen. That's all the questions that I have prepared. If there's nobody else with one in the audience, then this will conclude this session of Ask the Expert. I would like to thank all of you for attending, and most especially I would like to thank our 4 experts here, and if you could join me in thanking them as well.
I hope I didn't. No. I'll give it to the other direction like you did. Baking sausages.
Is making sausages.
Yeah.
Clearly have the formula.
You've heard the story of the 2 butchers who meet every day in the town square to play chess. And they each bring their lunch.